Okay, so now we can do the metrization theorem. And no, we're not going to construct a metric. So what we're going to do is show that it can be embedded into a metric space. And so then it just inherits the metric space. So the metrization theorem, again, it came out of that sort of Soviet school. So it was published posthumously by Urysohn, who died in 1924. It was published in 1925. He actually said every second countable normal space is metrizable. And Alexandrov a year later said, well, we really meant to say regular here because if it's second countable regular, then it's normal for free. And so really we like to categorize things with if and only if statements, right? So we have second countable regular space is metrizable. Now we know that all metrizable spaces are perfectly normal, right? So there is, because of the distance, you've got your balls centered at a point of whatever radius you like, that just separates outer spaces as good as you want, right? So you really can't get anything better in separation than the metric space because of the distance. All separable metric spaces are second countable, right? Because separable means it has a dense subset, a countable dense subset. So you just take your countable dense subset and put balls of rational radius, and that gives you a perfectly good countable basis. However, there are metric spaces which are not second countable. So for example, anything with the discrete metric, any uncountable set with the discrete metric is going to be not second countable, even though it's going to be first countable, right? Because just a singleton point is a local basis. So, okay. If you want something which is not so trivial, think of the set of bounded real sequences in the super norm. That's a perfectly good metric space, and of course, there's no way that we can get a basis for the whole space. Although, of course, at any given point, we can have a local basis. So it's so all metric spaces are first countable, right? Because just at that point, you just take the balls of radius, of rational radius, and that gives you your local basis. Okay. So second countable is good. First countable, however, is not going to be good because remember this space here is the lower limit topology. It's completely regular, it's first countable, but it's not metrizable. Right? So that kind of is a counterexample that stops us going the other way. So what happens is, so this was a kind of a project for a while to completely classify, figure out what a metrizable space was, and that answer came in 1950-51 when there were two independent papers which proved the same result. Nagata, so there's been a Japanese, especially after the Second World War, Japanese mathematicians were strong in topology and differential geometry. Smirnov, of course, is a Russian. He was actually a student of Alexandrov, who was Urysohn's partner. So that's definitely part of that Soviet school. And they said they came up with a space is metrizable if and only if it's regular and has a basis that is countable and locally finite. Okay. So we won't go into that too much because we're not actually going to prove this. But I just gave the definition there. So a collection of subsets is locally finite if every point has a neighborhood that intersects only finitely many elements of that neighborhood. And we call a collection countably locally finite if the collection is a countable union of collections, each of which is locally finite. That seems like a lot to get around. But the fact you've got this BN here should be kind of a clue that it's somehow going to give you a metric somehow. So, you know, we don't have to go into the detail. So I said, we're going to do 34.1. We're not going to do section 40. So this idea of having a basis that is countably locally finite is kind of like a notion that lies between first countable and second countable. So it's basically what they came up with, these guys came up with as the right countability axiom for this theorem. So so actually you can think we could restate this theorem as a topological space is separable and metrizable if and only if it's second countable regular. Right, because so if it's second countable and regular, we know it's metrizable. If it's second countable and regular, it also has to be separable, right? Because using second countability, we can generate a separable set out of that. So it goes both ways. So what really this theorem does, it just extends this to the non-separable case. So we really do understand when you have a metric space. So this gives you like a really good topological way to categorize metric spaces. Okay. So how we're going to prove this is we're actually going to prove it two ways. And the reason why we do that is the two different proofs give two different directions to go. The first way, we're going to embed our second countable regular space into R omega in the product topology, which you know is a pretty good metric space. And then we can generalize that to a nice embedding theorem. And the second proof is done by embedding X into unit interval to omega in the uniform topology. And we're not going to really do anything with that. The only thing is that that's the construction that's needed to prove this theorem. And so it was basically the key step in proving that. Okay. So before we start, we have to have a proving lemma. Okay. So the metrization theorem is actually not that hard. The big leap, the really deep result comes. We've already seen that was the Urysohn lemma. That was when we saw that these spaces, that normal spaces have enough continuous functions to, and so this definition here sort of like kind of makes that more explicit what we mean by having enough continuous functions. So let's just say we have some family of functions from our space X, and they don't all have to go to the same topological space. Right? The family is said to separate points in X if for each disjoint set of points, there's a function such that f of x doesn't equal f of y. It's kind of like sort of like a Hausdorff kind of condition. Okay. A collection is said to separate points from closed sets if for each point in X is each closed set such that our point is not in the closed set, there's a function such that f of x is not in the closure of f of a. Of course, A is closed, but of course the image of A doesn't have to be closed. And you can kind of see, if this is kind of like a Hausdorff condition, this is kind of like a regular condition. So, so what the Urysohn lemma tells us then, if we've got a second countable regular space, then there is a countable collection of continuous functions from X to the closed unit interval that separates points from closed sets in X. And so that's what we mean by saying that there's enough continuous functions. Of course, we say second countable regular. Second countable regular set, of course, is normal. So this is really what we mean when we say that a normal space has enough continuous functions. Okay, so how are we going to do that? Well, in second countable, that means we have a countable basis for X. And so what we're going to do to show this lemma is that given any point and any neighborhood of that point, that there is an element in our family. Right, so we've got to, so how much, I've got to say, we've got to construct this family that's going to be positive at x naught and vanishes outside U. And if you see that, that's kind of equivalent to separating a point from a closed set, right? Because it vanishes outside of U, that means it vanishes on this closed set. And so that means we are separating x naught from that closed set. Right, because if you have a closed set A when x is not in A, then of course x minus A is going to be the neighborhood of x. So it's the same kind of thing. Okay, so it's second countable regular. So by the theorem that we proved earlier, we know x is normal. So that means we can apply the Urysohn lemma. So that means whenever we have, I didn't say what Bn, so Bn is our countable basis. So if we have one basis element closure contained in another basis element, then by the Urysohn lemma, we're going to get a continuous function that is going to be 1 on this closed set, and it's going to be 0 outside of Bm. So we kind of have a picture that kind of looks like this. So we have x, we have Bm, And we have Bn. And we're going to have the closure here. Blue chalk here. So by the Urysohn lemma, we can, so here we've got a closed set. Here is our other closed set that lies out, right, which is x minus bm. That's our two closed sets. So the Urysohn lemma says that we've got a function, continuous function, that's 0 on one and 1 on the other. Okay. So for each kind of thing, we have a pair of points. So let's call that G and M. Okay, so given any point in X, and given any neighborhood of that point, we know that there is a basis element containing that point and contained in our neighborhood. And then by regularity, some theorem we proved before, we also know that there is another basis element, Bn, containing X naught, such as closure is contained within Bn. Okay, and so that gives us then our collection of desired functions. And our desired function is going to work for every point and every neighborhood of that point. There is going to be some GNM, which is where this is going to hold. The only technicality, of course, is it's a pair, so it's indexed by Z plus cross Z plus. So, but that's countable, so we can just re-index it. And we're going to just call that F. Okay, and so that's really the hard part of the theorem. It's coming up with these functions, and those functions come up because of Urysohn. So this was really Urysohn's really bright idea that made all this work. And if you do other things in topology and differential geometry, you'll see that when you have these kind of collections of functions like this, they turn out to be a really powerful tool that you can do a lot of stuff with. Okay. So how are we going to embed X in R omega? Well, it's pretty simple, right? We're going to take R omega, the product topology, and we're going to define our function X to R omega, just like f of X equals the function whose component functions is that family that we just constructed. Okay, and so what are we going to do then? To be done, we're going to show it's continuous. It's an embedding, so we've got to show that it's a continuous bijection onto its image, and we need to know the inverse is continuous, so that we have a homeomorphism between X and f of X. Okay. Well, the fact that it's continuous is easy is because we're in the product topology and all the components are continuous. So our map is continuous for free. It's injective, right? Because because we know our family separates points from closed sets, it's definitely going to separate points, right? There's going to be some index such that Fn of x is positive and Fn of y is 0, right? Because we can separate them. Okay, so really for free, without doing anything, we've got that F is a continuous bijection from X onto its image. So the only thing we really have to show is that it's an open map. And so that means that the inverse is continuous. So if we have an open set U in X, we need to show that F of U is open in the image. And that's not really so hard at all. Here's a little picture here that we need to show. Okay, so what does the picture show us? So really, okay, so we have some open set and we want to show that its image is open. So let's say we have a point in our open set. And so that means we have a point in the image. Okay, so Z naught equals f of x naught, that's in Z. So here is the picture here. So here is our x, here is our R omega. Here's x naught, it gets sent to Z naught. Okay, so again, we use the fact that our family separates points from closed sets. We can choose an index such that the function is positive at x naught and at x minus u, this closed set, the function is 0. Okay, so we've got a kind of situation like this over here. Okay, so what we're going to do then is look at the positives, the positive reals, and look at pi inverse then n of this. Okay, so let that be the set V, and let W be V intersected with Z, V intersected with the image. Right? So that's an open set in the image because V is an open set. Right? Because it's the inverse image of an open image. Okay, so we know that our point Z naught is in W, right? Because pi n of Z naught is equal to Fn of x naught. So it's equal to and we chose that to be greater than 0. But W is contained in F naught because if Z is some other point in the image, right, which is in our W, which has a positive the value here, right, pi n of Z is 0, then X must be in U, so Z has to be in FU. So that shows that the set is open. So basically here we've got, here is our 0 to infinity thing here. It gets put in here. Z naught is somewhere on this interval. Because it's positive, there has to be things less than it. And that gives us our open interval. So that's not really so spectacularly hard. Okay. So as a corollary to this, we get the following embedding theorem. So if we just look at our proof here, right? if we just look at how we did our embedding, we didn't really use, the only point where we used regularity and normality, right, was in coming up with our family of functions. So in the actual proof in the embedding here, the only place where we really used anything was to show that this map was injective. And the only thing we used there was the fact that the space has to be T1, that points have to be closed for us to be able to separate out points. So it follows then that if you've got a T1 space and you've got any family of continuous functions that separate points from closed sets, then you do exactly the same thing. You're going to get an embedding of our space into this product of the reals. And this is, of course, in the product topology. Right, so all we've done is really replace omega. We've dealt with integers and omega. Really, this works for any index set whatsoever, J, which we index with alpha. And once we had this family of functions that separate things, all we needed was T1. And if f alpha actually maps x into 0, 1, then we can actually embed x into some product of the of course, I said that in the space we only needed T1, but the fact that we can separate points from closed sets means it's better than T1, right? And in fact, the fact that you can separate points from closed sets, that's basically the definition of completely regular. Right? Completely regular means that you've got a function which is 0 at a point and 1 on the closed set. So kind of the nice thing, another nice corollary then is we get a categorization of what completely regular is. So the completely regular spaces are exactly those subspaces of 0, 1 to the j for some index set j. Right, because remember, completely regular means that we have a function which is 0 at a point, or 1 at a point and 0 on our closed set. Okay, the second version of proof, let's do something with the uniform topology. So now we're going to embed x into 0, 1 to the omega in with the uniform norm. So notice back in this theorem here, we didn't really, like in the proof here, we just said R omega. And so really we could have done 0, 1 omega, but it doesn't really make that much difference. I mean, if it's in 0, 1 omega, it's definitely in R omega. And of course, zero, 1 omega is homeomorphic to R omega. So That's a perfectly good subspace as well. So the fact that sometimes we talk about R omega and other times we talk about 0, 1 omega really doesn't mean that much. But it is important for this proof that we do 0, 1 because we're dealing with the uniform metric. So in the product topology, it didn't make much difference whether we talked about R omega or 0, 1 omega, but with the uniform metric, it does make a difference. Okay, so we start off with exactly the same preliminary lemma. We come up with a family of functions that separate points from closed sets. But now we do the following thing because we're dealing with the uniform metric. We replace Fn by Gn, where Gn is just Fn divided by n. And you can already kind of guess why we do this, because we don't want to be, because we're dealing with the uniform metric, we don't want the tail to cause us problems. So we just divide by n. Okay, so if we do this, then Gn is still a function from x to the unit interval, but it's even better, right? Gn of x is always going to be less than or equal to 1 n for all x. Okay, and so now we define our function in the same way, and I called it capital F, I didn't change it to capital F, just to be the function whose component functions are now the Gn. So this is basically the trick that Nagata and Smirnov came up with in 1950 to get this to get their theorem. So we get certain things for free, right? So just as before, F is injective for the same reason. F is an open map for the same reason, right? Because the uniform topology is finer than the product topology. So if a set is open in the product topology, then it's open in the uniform topology. So the only thing we need to show is that F is continuous. And because we're in the uniform topology, it's no longer enough to say that the component functions are continuous. And this is basically the reason why we divide by n to make this thing work. Okay. So we finish up with just a classic proof of continuity, which did in advance. It's like something you would have done through in advanced calc. Okay, given a point, given an epsilon greater than 0, we choose n large enough so that 1 on n is less than or equal to epsilon on 2. Okay, so you kind of should be able to figure out where this proof is going. We're going to break it up into 2 bits. We're going to do it. We're going to treat the start, the first few things in the function, and then we're going to treat the tail. Okay. So since we've only got a finite number of things, like we're only interested from 1 to capital N, we can use the continuity of our component functions to come up with a neighborhood such that the difference between the function at x and the function at our base point is less than epsilon 2 for x in UN in our neighborhood. Then we just let U be the intersection of all these neighborhoods. It's non-empty, right? Because x naught has to be in there, and it's still open because it's only a finite number of intersections. And so we're done, basically. That's it. U is going to work. If n is less than or equal to capital N, then by our choice of U, we have this. We have the difference between these is less than epsilon 2. Whereas if n is bigger than capital N, then since the image of x lies in this little tiny interval, then the difference between these two things has to be small just because it's got nowhere else to go. So it's less than 1 n, and that's less than epsilon 2. So at every component, the difference between gn of x and fn of x naught is less than or equal to epsilon 2. Hence, for all x in U, we have the metric between these things has to be less than or equal to epsilon 2, which of course is less than epsilon. So that wasn't that difficult either. That's just a normal proof of continuity. So really the hard stuff was coming up with the functions and realizing that having this family of functions that separates points from closed sets is enough to prove it. And so you see we've gone nowhere near finding a metric. Okay. All we've just said is it's a subspace of these spaces, they're metric spaces, so therefore it has a metric there. So when we pull back with the homeomorphism, it's going to have a metric there. Who knows what it is? And that's enough for today. Any questions about that? I know, it's just like, that's because we've done all the hard work before. So, and this is actually, I think we're going to be able to coast for a little while because we've done all that hard work and now we're just going to reap the benefits of the hard work. Yeah, this, as I said, this could have been in advanced calc, this proof, really.
Maybe.
Well, I mean, if you had the background.
If we had a little more from the topology definition.
Yes. Okay. And